Welcome back, everybody. In today's lecture, I'm going to be showing my solution to the lab exercise that we had yesterday. So when you click on the lecture notes for today's lecture, at the top of those lecture notes, you'll find a button that will allow you to download a copy of the project that has that solution in it. And today I'm going to be covering key parts of that solution. I won't be covering absolutely everything in the solution, so if you want to see how other parts of the solution are supposed to work out, by all means go ahead and download my solution and take a look at that. All right, so let's go into the solution and start talking about some bits of interesting code that you'll encounter there. The first method that I want to talk about today is probably the single most important method in the entire project because it is the method that is at the heart of implementing the strategy that we have of searching through a maze. And a key part of the search strategy is at any given point in time, when you find yourself somewhere in the maze, the natural question you're going to ask is, well, where do I go next? And the method that is responsible for answering that question is the find open neighbor method in the maze class. All right, so let's start talking about that very important method, which plays a key role in finding the solution. Okay, so the way this is going to work is you're going to be already sitting at some location in the maze, and that location is described by a cell object. And we're going to be handing that cell object to this method as a parameter to work with. All right, and the very first thing that we'll do with that cell when we receive it is get some more specific location information. It turns out that the cell class has built into it a couple of handy methods that you can call to determine exactly what row and what column that particular cell sits in. And we're going to be doing our search relative to that location. Okay, now when we talk about neighbors, what we're talking about is the four possible directions that you can go from that location. You can go either up or down, or you can go left or right. And both of those, all four of those involve making a small change to either the row or column number to get you to a different cell. Right, now what we're going to do next is we're going to write a set of 4 if statements, one for each possible direction that you could search in. And if any one of these if statements comes across a neighboring cell which is currently declared to be open and available for us to travel to, we're going to immediately stop and return that cell as the result of our little search. All right, so the first example here is the logic, which is basically, which involves looking up from where you are now. Looking up from where you are now basically means going one row up from where you are now. So if you know what row and column you're currently located in, if you go to that row -1 and that same column, that gets you to the cell directly above where you are now. And if we can go to that cell and ask it whether or not it's open, if it says yes, at that point we can immediately stop and declare success. And all we would do at that point is return that cell that just told us that it's open. Right? And of course, we use the same strategy for all 4 directions that we could possibly search in. Right, now, there is one other aspect to this method that you'll discover, because if you go ahead and write the code for this method, a thing that is very likely to happen, in fact, very quickly when you start trying to use this method, is that you may start getting some exceptions thrown from this method. And the reason that you may get exceptions has to do with the fact that there are certain locations in the grid that are unusual and are unlike other locations in the grid. Specifically, the locations I'm talking about are all of the locations around the perimeter of the grid. Right, now, what makes all of these locations unusual is that in any of the locations on the perimeter, you don't automatically have 4 directions that you can go in. So for example, if you are sitting at a cell which is on the left edge of the grid and you try going left from there, when you try doing that, you're literally going to fall off the grid. So in this logic here, if I tried going left from a cell that is at the left edge of the grid already, and I try executing this code, the instant I execute this bit of code, which is asking for the location in the grid, which is just to the left where I am now, that's going to throw a particular type of error. It's basically called it's going to generate what's called an array index exception. Because if I'm already sitting at the left edge of the grid, I already find myself in column 0. And if I try going to column 0 minus 1, which is column -1, that's an illegal location that isn't in the grid. And in Java, anytime that you try accessing an illegal location in any sort of an array, that is going to throw an exception. All right, so if you try running this code without any sort of special test to prevent that problem, you would run into these problems around the perimeter of the grid. All right, so what we're encountering here is a phenomenon which is widely known in computer science, and what we've just encountered is an aspect of what computer scientists called an edge case. Because very often in problems, when you're dealing with different scenarios, very often what you're going to find is the problem naturally breaks down into two cases. One case is what we might call the usual case. These are the cases where nothing unusual happens. In this problem, the usual cases are all of the cells that are somewhere in the interior of the grid. If I go to any one of those usual cells and try looking in any four of these directions, nothing bad will happen to me. So that's sort of the usual case. In addition to those usual cases, we have what computer scientists called edge cases. And in this problem, the edge cases literally are on the edge of the grid, and those are any of the cells that are around the perimeter of the grid. And the problem that all of those cells have is that for any of those cells, there's at least one direction that if you try looking in that direction, you'll actually fall off the grid. And when you try running that code, you'll generate an exception as the program is running. All right, so those are unusual cases. They're commonly referred to as edge cases. Now, as soon as you realize that you have edge cases in a problem, what you have to do to respond to that is you have to start setting up a system of tests that are designed to distinguish the usual cases from the edge cases. And whenever you catch an edge case, you have to respond to that in the appropriate way. Right now, in this particular problem, handling edge cases basically is going to involve slightly restructuring the if statements that I write. Right, so for example, here where I would like to write an if statement that looks one row up from where I am now, before I can actually execute that part of the test, I need to do another test, and that is to simply ask, does that correspond to a legitimate location? All right, and the way you would do that is by adding another part to the test, and the purpose of this other part is to tell whether or not we are actually in one of these edge cases. Right, so if I'm in the edge case where currently I'm at the very top of the grid and I'm trying to look one row up from there, I can tell that I'm going to be in an edge case by simply comparing the value of row -1 to 0. And if the row above me, row -1, if that is anything greater than or equal to 0, that means that that direction is not going to be a problem to look in. And once we pass that test, then we have established that it's safe to go ahead and look in that direction and ask for the cell that sits one row above us, and then finally ask whether or not that cell is open. All right, so this is a classic example of how you handle edge cases. Once you realize that you have the potential for edge cases, what you need to do is add some additional tests. In this case, the way I added the additional test was basically by adding another part to the if test that checks to see that we are not in an edge case. And if we're not in an edge case and it's safe to look in a particular direction, then I go ahead and look in that direction and ask what I want to ask anyway. All right, so that's an important special feature of this method because this problem has the potential for edge cases existing in certain parts of the grid. We have to explicitly test for those and make sure that we're not in one of those edge cases each time that we start looking in a particular direction. Okay, so that's what's especially significant about this method. You have to explicitly add additional logic to look for those unusual cases and handle them. And then once you've done that, you have a complete solution to what we're trying to do here. Okay, so short pause here and ask if anybody has any questions about this particular method here. Okay, now the next thing I want to talk about is the path class. Another part of the exercise in this week's lab is filling out all of the methods in the path class. So let's take a quick look at that class next and say a few words about what's going on there. Okay, now as I mentioned to you in the lecture on Wednesday, the key thing happening in the path class is that a path is basically a list of cells. And the way that we're going to be implementing that list of cells is by using an array list. Right? So the first and most important thing about this path class is that it has embedded in it an array list that will store a list of cells for us. Right? And then once you realize that you are working with an array list, the code for most of the rest of these methods boils down to doing various useful things with that array list. Right? And that in turn means using several key methods that come along with the array list class. In this code, you're going to see me using three different methods. You're going to see me using the get method, I'm going to be using the add method, and I'm going to be using the remove method. Those are all three methods that are available in the array list class, and they will help me do the various things that need to be done with my path. Right, so a trivial example of this is the add cell method. This is designed to add another cell onto the end of the path. And once somebody hands you a cell, the only thing left to do is making sure that you add it to the array list. And that gets done in a very straightforward way by using the array list add method. We simply say, here's a new object, please add this object to the end of the array list. Likewise, the method for removing a cell from the end of the path, that's going to involve the use of one of the remove methods in the ArrayList class. It turns out the ArrayList class actually has two different remove methods. One of these remove methods allows you to remove something based on its index or its location in the list. And the other remove method allows you to simply hand it an object and say, hey, I know this object is somewhere in the list. Can you go ahead and remove it from the list for me? Right now, in this case, probably the easier of those two is to use the version of the remove method that does everything based on the index. And since we know that what we're going to be doing is we're going to be removing the last item from the list, we can easily get the index for that last item by taking the size of the list and subtracting 1 from it. Right? Remember, we're operating with a zero-based system here, so that the last item in the list is always at location size minus 1. Right? And once we've computed that index, all we have to do is pass that index to the remove method, and it will then do its work of removing that object from the array list. All right, and a similar thing is this method here, where we want to return the last cell in the path. Once again, there's a method in the array list class that will help us do that. There is a get method available in the array list class, and it works using an index. All right, so once again, we have to compute the index of the last item in the array list. We pass that index to the get method, and it will hand us the object that is actually sitting at that last location, and that is finally the thing that we return from this method. Right, so that's the name of the game here in the path class. And in the path class is to quickly fill in all of these methods, and to help us do all of our work, the ArrayList class is going to have a bunch of useful methods that will allow us to do all of these things in a fairly direct way. All right, and finally, one last sort of slightly more sophisticated example is this print method. The purpose of this print method is to print everything in the path. Well, here's an opportunity for us to use a trick that we saw a couple of lectures back. Here's a chance to use an enhanced for loop. Since an array list is one of the collection classes in Java, and all of the collection classes allow you to write enhanced for loops, this was a natural opportunity to do something like that. So here we're saying, for every cell C in the list of cells that we have, let's do something with that C. In this case, let's go ahead and print it. And since cells are capable of turning themselves into strings automatically, all we simply have to do is hand a cell to the print line method, and it will go ahead and print that cell for us. All right, so that makes it very easy to print the contents of a path. Okay, now the next thing that I want to comment on is a practice that I started doing in this example, and that is the practice of adding a main method to every one of the classes with the intention of writing a short test program that allows us to test each of these classes and see whether or not they're working correctly. All right, so one of the things that I did for you in the materials that I prepared for the lab is I started the job of writing the main method for the maze class, but I left it to you to go ahead and add some additional parts to that that would more thoroughly test the maze class. All right, so here I've gone ahead and done that. This is the main method that is embedded in the maze class. And its main purpose is simply to test various aspects of the maze class and verify that they're working correctly. All right, so what you'll see happening here in the code is some code that creates a maze. We'll go ahead and print it to verify that it was read successfully from the file. And then we'll do some additional operations. A couple of very important operations that we need to test are the operation for finding the entrance. So I'm going to call that here and get the cell that sits at the entrance. And then to confirm that that worked correctly, I'm going to go ahead and print that entrance cell. And then the other important operation that I need to test here is the operation of finding an open neighbor next to whatever cell you're currently at. And this is also a great opportunity to make sure that my edge detection code is working correctly, because in this example, it turns out that the entrance cell is one of those edge cells. It's sitting at the edge of the maze. And if you didn't write your find open neighbor method correctly, what may happen when you try to find an open neighbor next to the entrance is you may get an exception if you didn't test for those edge cases and weren't checking to make sure that you handled those correctly. All right, so there's an example of a short test program that you might write and embed in a particular class with the motivation of making sure that that particular class is working correctly. All right, and of course, so we can go ahead and run that just by right-clicking and choosing the option to just run this file. That will run the test program for the maze class, and that will allow us to confirm that everything is working correctly. All right, so here it correctly prints the maze. It confirms that the entrance is where we think it should be, and then finally it is able to successfully find one of the neighbors of the entrance. All right, so that increases our confidence that the maze class is functioning correctly, and that in turn will give us more confidence when we go on to the next few stages of the project. All right, and again, as I'm going along here, feel free to interrupt me at any point with any questions that you have about anything that I'm doing. Okay, so that is the test program in the maze class. All right, now I've also written a test program in the path class with exactly the same motivation. The motivation again is once we've constructed a class to go ahead and test it and see that certain operations are working correctly. All right, so in this test program, what I'm going to be doing is I'm going to be creating an empty path. I'm going to create a couple of cell objects. I'm going to add those to the path by using the add cell method. And then I'm going to print the path to make sure that the cells I added were successfully added. Then I'll go ahead and ask to remove one of the cells. And then finally, I'll print the path again. All right, so this is, again, exercising various of the methods that are in the path class to confirm that they're working correctly and increase our confidence that this part of the project is working the way that it should. Right? And again, if I run this test program, it appears to be working correctly. So we see now that we've successfully added those two cells to the path. And then when I ask for the last one to be removed and I print the path again, that has given me the answer that I'm looking for. All right, so again, this is a very useful practice, especially anytime you find yourself writing a program that features multiple classes. It's always a good idea to test each of the classes individually to make sure that each individual class is working the way that we expect. And that's a useful step to do before you get to the final stage where you put everything together and you confirm that everything is working the way that it should. Okay, so now the only thing left is putting all of this together to solve the original problem. Again, the original problem is, can you find your way successfully through a maze from the entrance to the exit? And for that, we have one last piece of code that needs to be written. Okay, now I have already written main methods in every single one of my classes. And because I already have one main method in every single class that I've written, if I'm going to write a main method that does the actual search in the class, in the maze, I'm going to have to basically create a fourth method just for that purpose. So that's what I've done. I've added a fourth class to the project. And the only purpose of this class is simply to give me another place in which I can set up a main method. And this main method is the one that will actually solve the problem that we're interested in solving. All right, so here is the code to actually do the entire maze search. All right, so, and as you can see, the code here is actually not very long. One of the reasons why the solution code here can be as short as it is that we've already done quite a lot of the heavy work in the other classes that we've written. In particular, in the maze and path classes, I've done a lot of work in setting up methods that are going to be useful to me when it comes time to solve the full problem. And the fact that those methods are already available and doing so much of the work for me will mean that by the time it comes time to write the full solution, I don't have to write an awful lot of code, because I can simply recruit all of these different methods that I've set up to help me do some of the harder aspects of what needs to be done. Okay, so that explains why the code here is relatively short. So let's now dive into the code and see what various bits of this code actually do. All right, so first, of course, we have to have a maze object, and here's the usual way to create that maze object. We also, of course, will need a path object, so that's a second object that we'll need to create at the beginning of the process. Okay, now the whole search process begins at the entrance to the maze. All right, so here we get to take advantage of the fact that the maze class has a method that will find that entrance for me. All I have to do is call that method and assign its result to a variable. All right, and I'm going to use this variable throughout the entire code here. This is a variable that will always be storing the end of the current path. And in fact, as soon as I take that cell and I add it to the path, that will in fact be the end of my current path. Okay, now most of the actual work of searching through the maze and finding our way to the exit is going to be done by a loop, right? And most of the rest of the code here is that loop to carry out the search process. Okay, now anytime that you write a loop, the first thing you're going to think about is, what should I use for the loop test? All right, well, here we have a fairly natural test that we can apply, and that is the search obviously needs to continue until the end of the path has made its way to the exit. Right, so this is the obvious test to apply to tell us when we're done, because whenever we look at the end of the path and we discover that the end of the path happens to be the exit cell, then it means that it's time to stop. All right, now remember, in a while loop, the purpose of the test is to tell us not when it's time to stop, but when it's time to continue. And in this scenario, it's time to keep searching as long as the end tells us that it is not the exit. All right, so as long as we haven't yet reached the exit, we have to keep going and the loop has to keep running. Okay, now on each round of this loop, what we're going to be trying to do is we're going to be trying to move our path forward. And the way we do that is we take the cell at the end of the path and we ask for an available neighbor next to that cell that will allow us to make further progress. Right, so here again, I get to take advantage of the fact that the maze class has a very powerful method that will do that search for us. We simply tell it where we are now, and it looks around and it tries to see if it can find an open cell nearby where we can go to next. Right, so it's just a simple matter of calling that method and then storing whatever cell comes out of that method into a variable so we can then examine that and do useful things with it. Okay, now the first thing we need to worry about is that in some cases, when you ask the maze to give you an open neighbor, in some cases it will not be able to find an open neighbor and it will return a special value of null to you. Right, so that's the first question you need to ask after getting this next cell. You simply need to ask, is that next cell null? Right, because that signals the fact that there is no place available for us to go. And in that scenario, essentially what that means is that we've wandered into a blind alley in the maze, and it's time to start backtracking out of that blind alley. And a simple and appropriate way to respond to that is to say, okay, if we find ourselves at a place where we can't go any further, the only remaining option to us is to try backing out of where we are now. And the way we would do that is simply by removing the last cell from the path. That's how we actually do the backtracking. And then once you have removed that last cell, you're going to have a new value for the end cell, right? So you have to come back and say again, okay, now I know there's going to be a new cell at the end of the path. Go ahead and tell me what that is so I can declare that to be the new end for my path, and we can go on from there. Right, so that handles backtracking, and backtracking will happen in any scenario where you try to move forward but discover that you can't move forward. Right now, if you instead ask for an open neighbor and you do get an open neighbor, you get a result here which is not null. In that case, what we'll want to do is head off in that direction. So what we do then is we take that next direction where we would like to go, we mark it as being visited, and we add it to our path. And then since this now is going to represent the new end for our path, we update our end variable to say this is now the new end of the path. All right, and those two simple operations, either backtracking or moving one step forward, are really all that we need. And if we simply do those operations over and over again, one of two things will eventually happen. Either we will find our way eventually to the exit and the loop will finish, or we'll reach a point where we can't go any further and bad things will happen to us. Right now, in this scenario, I already know that there is in fact a path from the entrance to the exit. So I was able to predict in advance that this code would actually complete successfully. But if you want to handle the possibility of wandering into a maze in which there is actually no way to make it to the exit, what we would need to do is we would need to add some additional logic to this loop to check for that scenario and handle it in some reasonable way. Right. I chose not to do that in this case because I knew in advance that the maze that we would be working with does in fact have a way to get from the entrance to the exit. But if you did want to make this a more general solution, you would have to add some additional logic here to check for the case where you can't find your way successfully to the exit. All right, but assuming that everything works out well here, eventually what will happen is we will eventually work our way to the exit. That will cause the loop to finish. And the only last thing left to do is simply to tell the path to print itself so we can look at the path and judge for ourselves that this looks like a legitimate path that gets us from the beginning to the end. Okay, once again, a short pause here, opportunity for questions. Does anybody have any questions about the logic that I've just shown you here? Okay, well, if not, the last thing for us to do is to simply run this and confirm that it works. All right, so, and here's the results that it spits out. The paths printing method prints these cells one per line. So here we can confirm that the first cell in the path is the entrance cell. The last cell in the path is the exit cell. And if you have the patience, you can look at all of the row and column numbers and actually trace the path through the maze itself and confirm for yourself that this is in fact a legitimate path that gets you from the entrance to the exit, right? And we can declare success here. Okay, so that is my solution to the lab exercise for this week. Again, since this was an optional lab exercise, you are not going to be turning in your work, so that's why I'm free to show you my solution here and share my solution with you. Okay, now where we're going next is in next week's lab exercise, we're going to have another lab exercise that has a lot of features in common with what we did this week. Once again, in next week's lab exercise, we're going to be dealing with a problem that involves implementing an algorithm. Part of this algorithm is going to be requiring us to work with array lists. So we're going to get some additional practice working with array lists. And we're also going to get ongoing practice working with objects. You're going to need to create at least one class in the problem for next week, and that will give you further practice working with objects. Now, one significant way that the exercise next week is going to differ from this week's exercise is that in this week's exercise, precisely because we had quite a lot of classes that needed to be written, I went quite a ways toward writing the code that you would need. So for this week's lab exercise, I provided a lot of the code ahead of time. I gave you the complete code for the cell class. I gave you roughly half the code for the maze class, and then left you with the job of filling in the remaining parts. Now, for the exercise next week, I'm going to be providing you much less code to start with, and more of the workload is going to be on your shoulders to actually write all of the necessary classes and the methods needed to make everything work. All right, so in next week's lab exercise, we're going to be finding ourselves in a situation where I'm going to be providing you much less code to get started with, and much more of the workload will fall on you to write the code that you need. Right now, the trade-off that hopefully will make that a little bit more doable is that the algorithm that we're going to be implementing next week, I think, is a little bit simpler than the algorithm that we implemented this week. And because it is a slightly simpler algorithm, there will be less code overall that you'll need to write to get the algorithm to work correctly, and that will make life a little bit easier for you.
ที่ทำอะไรอยู่
Hello? Okay, so does anybody have any questions at this point about what's happening next week or anything else related to what we just talked about here? Okay, so if not, I will wish you all a happy weekend, and we'll see you all back again on Monday. On Monday, what I'll be doing is I'll be giving you the background information that you need to do the lab exercise for next week, and then we'll go ahead and go on into the lab exercise after that. All right, so until then, have a good weekend.